Section 14.12 deals with analyzing fragments. If you go back to section 14.11, I'll just kind of back up here quickly. We talked about analyzing M+2 peaks. Namely, we talked about detecting chlorine in a molecule. If we have chlorine in a molecule, it means we're going to see an M+2 ion with a peak height that is 1/3 the height of the parent. And that's because chlorine has two isotopes, chlorine 35 and chlorine 37, which are in approximately 3-to-1 abundance or relative abundance. And then we talked about analyzing the M+2 peak for a molecule that has a bromine in it. And since bromine's two isotopes, bromine 79 and bromine 81, are pretty much equally abundant, roughly 1-to-1 or 51 to 49%, that means that your M+2 peak should be about the same height as your molecular ion, and we see that right here in this mass spec. Well, we're going to talk about fragmentation today. And if you remember, going back to the beginning of the section on mass spec, what we said is we were going to take a molecule, like let's say we take pentane, so 1, 2, 3, 4, 5, this is the bond line structure, and then you hit it with a high energy beam of electrons, so I think it was 1600 kilocalories or something like that, and then you knock an electron off, so you lose an electron, and then you end up with a radical cation, which we have shown here. And remember that the mass of the radical cation is going to be the same as, the just the uncharged species, because the mass of an electron is so small. Okay, so we would look for the parent ion, and if we want to calculate the mass of the parent, that would be C5H12. So we take 12 and we multiply it by 5, which gives us 60. So we have 60 plus 1 times 12, which gives us 12. That gives us a mass over charge of 72. So we should see our molecular ion having a mass over charge of 72. So I'll just put here mass over charge of 72. Now that might be the base peak and it might not, but that is our parent. Now, how is this thing going to break apart? How will it fragment? Remember, we're making a radical cation, and the radical cation is not stable, so it just falls apart. But again, the great thing about organic molecules is that they fragment in a predictable way. So what are the kind of fragments that we could expect to lose here? Well, if we lost a methyl radical, which is shown here, and remember, a radical is just a species that has an unpaired electron, and you can see that unpaired electron here, well, then we'd be left over with this carbocation here. This looks like a butyl carbocation. But what's the mass of the methyl radical? Well, it's got 1 carbon and it's got 3 hydrogens. So 3 times 1 gives you 3. So that's 15. So that means you would lose 15. Well, we can look for one of two things. Or actually, we're looking for one thing. If you take 72 and you subtract 15, you end up with, you should see a fragment with a mass over charge of 57. So we would look at 57 in the mass spectrum and we should see something there. But our rationale is this: we see this peak in the mass spectrum, but we know it came from the loss of a methyl radical. If you were at yesterday's lecture and you're wondering, why are you using whole numbers for your masses for your elements? Why are you using carbon with a mass of 12? Why aren't you using 12.01? That's what I used in General Chemistry 1. Well, remember, this is low resolution mass spectroscopy, and so, or spectrometry. And so for hydrogen, we only use a mass of 1. For nitrogen, we use a mass of 14. For oxygen, we use a mass of 16, so on and so forth. All right, well, what are some other radicals that we could lose? We could also lose an ethyl radical. Well, how much does an ethyl radical, what's its mass? Well, if we tally it up, we see that it has a mass of 29. So what's the mass minus 29? We take 72, we subtract 29, and we end up with 43. And that means we should see a fragment with a mass over charge equal to 43. So we look for that in the mass spec. And again, that would come from the loss of the ethyl radical. Hopefully you're getting the hang of it now. If we were to lose a propyl radical, it has a mass of 43. You take 72 minus 43, you get 29. So that means if we lose a propyl radical, we should see a fragment in the mass spec with a mass over charge of 29. And then finally, If we were to lose the entire butyl radical, well, then we see a fragment with a mass over charge equal to 15. And so all of those ions, those cations in the green boxes, they have masses of 57, 43, 29, and 15. But again, where do they come from? They come from the loss of 15, 29, 43, and 57. Notice that these are all odd numbers. I think that's pretty noteworthy. And these are numbers that you want to have in your mind. You want to remember 15 for the loss of a methyl. You want to remember 29 for the loss of an ethyl, 43 for a propyl, and 57 for a butyl. Now, if you're thinking, well, can't I just bring my calculator into the quiz and use that? And I could just tally it up every time. I suppose you could, but remember, the more that you understand something, the easier it gets. Another thing I just want to remind you of is that the mass spec, remember, it only detects charged fragments. You will not detect any of these radicals in the mass spec. Why? Because they do not have a charge. Now, when we're talking about pentane, this molecule here, this is just a straight chain hydrocarbon. What if we have something a little bit more interesting? What if we have something with some branches on it? So let's check out this compound here. So let's practice our nomenclature. We have 1, 2, 3, 4, 5 carbons. So this is some kind of pentane. This is 2,2-dimethylpentane. So 2,2-dimethylpentane. And its molecular formula, it's got C567, so C7H16. So what might its molecular ion be? So we have 7 times 12, which gives us 84. So we take 84, we add 16 to that, and we end up with 100. And so our molecular ion should have a mass over charge of 100, which is an even number. Well, how is this thing going to fragment? Now, if you're saying, well, Mr. Dion, you told me that you could lose a methyl radical. That could happen. You told me you could lose an ethyl radical. That could happen. You told me you could lose a propyl radical. All of those things could happen. Okay. Could I lose this? Sure. All of those things can happen. But what's interesting is this. Look, it says, while all fragmentations are possible and observed, the most abundant fragment is going to be the one arising from the most stable carbocation. Well, what do we know about carbocation stability? So if we put here carbocation stability, we know that a tertiary carbocation is the most stable of all, which is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl carbocation. So what radical would we lose to get the most stable carbocation? Well, if you were to fragment the molecule at this bond here and lose a propyl radical, right, which is M minus 43, because the propyl had a mass of 43, well, then you're left over with a tertiary carbocation. And that would be the most stable carbocation that you could get, or at least one of the most stable carbocations that you could get if you were to fragment this molecule. Now, there's some reasons why I think this would probably be the most stable carbocation, but the bottom line is if you take 100 and you subtract 43, you end up with 57. And so we should see a large peak, maybe even a base peak, with a mass over charge of 57 that arises from this tertiary carbocation. Now, if you're wondering, well, hold on, Mr. Dion, what if you lost a methyl radical? What if you lost this methyl radical or this one here? If you were to lose that methyl radical, then you'd end up with this. So let me just scribble it down here. You'd end up with a carbocation that looks like this. So let me have CH2, CH2, CH3. And that would come from the loss of a methyl radical. So this is M minus 15. Okay, so the loss of 15 would give you this here. And this is a tertiary carbocation. And so that would probably also be a very large peak in our mass spectrum. So we should see also something with a mass over charge of 15. Now, this is where some questions can start to pop into your mind. Like your mind is racing, you're trying to learn the subject. Well, do I have to know every single fragment that could happen? No, not necessarily. You need to know what would be the most abundant fragment? So something that would make a tertiary carbocation would be the most abundant fragment. Could you lose all of this and just end up with a methyl cation? Sure, but that's highly unstable, and therefore you would only get a little bit of that. All right, only a small amount of that. Now, if your mind is still racing and saying, oh, jeepers, how many different ways can this molecule break apart? The answer is quite a few, but the bottom line is that if you do the practice problems and the more that you look at mass spectra, the more familiar you will become with fragmentation and the more sense it starts to make. But the bottom line from this slide is that the most abundant fragment is going to be the one that produces the most stable carbocation. And in this particular molecule, 2,2-dimethylpentane, since the tertiary carbocation is more stable than a primary or a secondary, the M-43 peak, or maybe even that M-15 peak, would be some of the most abundant peaks in the mass spectrum. So those are the things you would look for. Well, the good news is, well, first of all, let me tell you that when it comes to fragmentation, I mean, there are people out there who are just experts in fragmentation and can look at mass spec and just, blow my mind and just say, this is from a loss of this is from a loss of that. But the good news is this. Look, I'll even skip the next two slides. We're going to come back to them. That in Chemistry 3101, you only need to know a few fragments. So this is Chemistry 3101 fragments that you need to know. The good news is we already covered most of them. We covered the first four: the loss of a methyl, the loss of an ethyl, propyl, or a butyl. There's only two more that we haven't covered yet. Okay, so don't get super stressed about it. There's not that many fragmentations or fragments that we look at in Chemistry 3101. We're just learning the subject. So let's go back and let's take a look at a couple of other types of fragments that are very common in mass spec. You can imagine why I started here. Why does the author of our textbook start with this? Because if you go here, a methyl, an ethyl, a propyl, and a butyl, these are some of the most common fragments that we see in a mass spectrum, especially in Chemistry 3101. Now, if we look at an alcohol, you see alcohols all over the place. It's a functional group and all kinds of organic compounds. And what's cool about alcohols is that they do very predictable fragmentations. There's two of them that you need to know. One is called an alpha cleavage, and the other one is just a loss of water. We'll come back to this one in a second, but let's start with what I think is the easiest one. Okay, if you take an alcohol, you bombard it with a high energy beam of electrons, you make the radical cation. This is your molecular ion. Well, that molecular ion will oftentimes lose 18 mass units. Now, where would I get 18 from? It comes from the loss of water. You are not expected to draw any mechanisms or, predict what the alkene would look like. I'm not going to ask you to do that on your first quiz. Okay, we're learning the subject, but the bottom line is, if you have an alcohol, alcohols can oftentimes lose water. So loss of water. And water has a mass of 18, so we oftentimes see a peak at M-18 for an alcohol. What do you notice about that 18? This is the first even number we've seen. And so all the other fragments that we looked at were odd so far. So when you see an even mass and it's 18, it usually means a loss of water, which would denote that you probably have an alcohol. The other one that is very common for an alcohol is what's called alpha cleavage. Now, before you get intimidated by all these arrows and say, what the heck is all of that? Okay, I'll make it as simple as possible. You do not have to know how to draw those three fishhook arrows. Do not worry about those at all. Don't stress about it. I'm not going to make you draw them. Here's what you need to know about alpha cleavage of an alcohol. Ready? I'm going to teach it to you very quickly. When you take an alcohol, right? If we were to draw this alcohol and draw proper Lewis structure, so let me just draw, oops, that's not very pretty. There we go. So we have our alcohol. We have the oxygen, which has 2 bonds and 2 lone pairs. You hit that with a high energy beam of electrons and bloop, you end up knocking off one of those electrons. So you end up with a radical cation. This is your molecular ion, right? This is your M+ ion. Well, you know the carbon that the oxygen is attached to of the alcohol? We call that the alpha carbon. So this is the alpha carbon. And what happens is that the bond between the alpha carbon and the next carbon can break. So we call that the alpha carbon. You could even call this the beta carbon. And if you're wondering, well, wouldn't this be a beta carbon too? Sure, yeah, that would be a beta carbon, but they're just showing the simplest possible cleavage here. All you need to know in this class is this: that bond can break. The bond between alpha and beta, and then the ion that you would see in the mass spec is going to come from the side with the alpha. Okay, the side with the alpha carbon, because the other piece, the piece with the beta carbon, is going to be released as a radical, and you don't see those. And if you're wondering, well, why would I see this side? Why would I see this? It's because you end up with a resonance stabilized cation. That's the reason why. And so alpha cleavage, again, just to review, you have the alpha carbon. It's the carbon that's attached directly to the oxygen. You're going to break the bond between the alpha, this is my beta carbon. You're going to break that bond, and the ion that you'll see will come from the side with the oxygen on it, and that's because you get a resonance stabilized cation. All right, so the last two types of fragmentation that you need to know, and then I promise fragmentation is over for today, are alpha cleavage of an amine, and then something called the Mclafferty rearrangement. You can see that we don't go into a ton of detail on either of them, since I fit them both onto one slide. Let me show you again. I'll give you the Coles or the Sparks Note version. What you need to know in Chemistry 3101 is that amines can undergo an alpha cleavage much the same way an alcohol did. We have the alpha carbon. It's the one attached directly to the nitrogen. Then you have a beta carbon. You break the bond between the alpha and the beta carbon, and the side that has the nitrogen on it, that is the ion you're going to detect in the mass spec. Why? Because not only is it charged, but why does it break in that way? Because you end up with a resonance stabilized cation. Now, if you're wondering, are you going to ask me to draw the resonance structures? I mean, resonance, this is something that we covered in chapter 2, so I would expect you to recognize a resonance structure when you see one. But the bottom line is that alpha cleavage is just the cleavage of the bond between the alpha and the beta carbon. And the last type of fragmentation is also pretty cool. It's called the Mclafferty rearrangement. So whenever you hear the word carbonyl in organic chemistry, I know that I taught you when we went over functional groups, I said a carbonyl is this, when you have a carbon with a double bond to oxygen. This is a carbonyl, so we call this a carbonyl. And you find carbonyls in esters, aldehydes, ketones, carboxylic acids, amides. We find carbonyls in a whole holy host of functional groups, even ones that we haven't looked at yet, like acid chlorides and anhydrides, and what else? Ureas and carbamates or urethanes, things like that. Anyhow, that's neither here nor there. But whenever we talk about just carbonyls generally in organic chemistry, and I know some of this stuff can be frustrating, but organic chemistry is an old science, and so there's a lot of things that just kind of stick around. Whenever they just talk about carbonyls and they mean it like a molecule, it means aldehydes and ketones. So aldehydes and ketones. Now, if you're going, why couldn't you have just written aldehydes and ketones generally undergo the Mclafferty rearrangement? It's because in our textbook, he just describes them as carbonyls. But if you just want to remember that aldehydes and ketones can undergo this kind of fragmentation called which is based on the Mclafferty rearrangement, then that's good enough for me. Now, if you're going, holy smokes, what are all of these? Do I have to draw this on a quiz? Do I have to recognize this? Good news. No. These, again, are fishhook arrows. These aren't even covered until chapter 10. So that will be the very end of the course. Do not worry about drawing this. How will you know you've got a Mclafferty rearrangement? Are you ready? Here's how you know. First of all, the requirement for a Mclafferty rearrangement is that you have a gamma carbon on an aldehyde or a ketone that has a hydrogen on it. Now, if you're wondering, what the heck is that? Well, here's a ketone. Right? This is a ketone here. You've got an alpha carbon, a beta carbon, and a gamma carbon, and you happen to have a hydrogen on the gamma carbon. If you don't have a gamma carbon, then you can't have a Mclafferty rearrangement. Okay, you've got to have at least a gamma carbon, and it has to have one hydrogen on it, at least. Then you can undergo this rearrangement called the Mclafferty rearrangement. You do not have to draw it, and you end up losing a fragment, okay? And you end up making this resonance stabilized radical. Now that resonance stabilized radical, you don't need to know how to draw that, but this is what's unique about the Mclafferty rearrangement is that you lose a mass, but so we'll put m minus x, but this x is an even number. It's an even number. Now, if you want to calculate the mass of this here, this is C6, and then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if we have C6H12, well, what's the mass of that? We take 6 times 12, which is 72, plus 12, which equals 84. So if you lost this, this would be, let me just say here, that if you were to lose this fragment, then you have an m minus 84, just in this particular instance. Okay, you're not always going to lose 84. It's just that it's got to be an even number. And the only other time that we see an even number being lost is when we lose water. So there's everything you need to know about fragmentation. What are the fragments you need to know? In Organic Chemistry 1, you need to know the loss of a methyl, ethyl, propyl, or a butyl, the loss of water, which comes from an alcohol, and the loss of something even, which comes from a Mclafferty rearrangement. And look, it even says here in the table, Dr. Klein put it himself, a ketone or an aldehyde. And let's add some information to this. We'll put here with a gamma carbon that has at least one H atom on it. Okay. So, and if you're wondering, like, what does that mean exactly? Well, look, if you had an aldehyde, okay, let's say you had this aldehyde, very simple aldehyde. This is called acetaldehyde. It cannot undergo a Mclafferty rearrangement. Why? Because it only has an alpha carbon. Let's say I had this. This is called propionaldehyde. It can't undergo a Mclafferty rearrangement because it only has an alpha and a beta carbon. You've got to have a gamma. Let's say you had this compound. This is called butyraldehyde. Butyraldehyde can undergo a Mclafferty rearrangement because it does have a gamma carbon. Now let's imagine that I took that gamma carbon and I put 1, 2, 3 methyl groups on it like this. So here's my gamma carbon. This cannot undergo a Mclafferty rearrangement because there's no hydrogens on the gamma carbon. And so you've got to have a gamma carbon with at least one hydrogen atom on it. So we'll put a hydrogen here, and this is our gamma carbon. And the same thing would apply for a ketone. If you have a ketone like this, it could undergo a Mclafferty rearrangement. But let's say you had a ketone like this. Son of a gun, what did I do? What have I done? All right, let's say you had a ketone that looked like this, where you just delete this and this, okay, like this. This could not undergo a Mclafferty rearrangement because you do not have a gamma carbon. On this side, you've got an alpha and a beta. On this side, you have an alpha and a beta. You've got to have at least one gamma carbon. I don't know why I put a delta. Brush up on my Greek alphabet. There we go. You need to have at least one gamma carbon in order for a Mclafferty rearrangement to occur. And remember, you lose something with an even mass. And there you have it, my friends. Those are all the different fragments that you have to know in Organic Chemistry 1. Any questions about those? Any questions about those fragments? All right, where are my students? Sorry, I'm looking at the chat. Okay, well, let's take a look at a question here and see if we can figure this out together. Remember, you're just learning the subject, so is it challenging? Absolutely, but when it comes to mass spec, we're just trying to get to the lowest hanging fruit. It says, identify 2 peaks that are expected to appear in the mass spectrum of 3-pentanol. For each peak, identify the fragment associated with the peak. Now look, we haven't done nomenclature of alcohols yet. So if I was to ask you something like this on a quiz, I would give the structure. Okay, alcohol nomenclature actually isn't even covered until I think something like the 2nd week of Organic Chemistry 2. So don't stress about the nomenclature of alcohols. If you need an alcohol, I'll give you its name. Okay, so let's see here. We've got 3-pentanol. Let me show you what it looks like. It's this compound here. Okay, so there it is. Our oxygen. Remember, the oxygen of an alcohol has 2 bonds and 2 lone pairs. If you want to draw out the entire Lewis structure, you know, with more detail like this, you can do that. But what are we going to do? We're going to take that molecule and we're going to hit it with a high energy. So we'll put here high energy beam of electrons, and then we're going to make a radical cation. So remember, we're going to lose one of the electrons off of the oxygen. What happens when you lose an electron? You end up with a positive charge. Okay, so there's our radical cation, and this would be our molecular ion. So molecular ion. And what would be the mass of this? You know, what's the mass over charge? Well, let's figure out what the molecular formula is for the parent. So it is, it's C5H12O. So C5H12O is what it would be. And if we tally up the mass, so that's 60 plus 12 plus 16. So if we take 72 plus 16, we end up with 88. So we have a mass over charge. Our parent has a mass over charge that's equal to 88. Well, how would this thing fragment? There's two possibilities for alcohols. Let's go back in our slides and review. When we have an alcohol, first thing that we would see is, or not first thing, but one of the things we would see is a loss of water. I think that's the easiest one. So if you take 88 and you lose 18, then you're going to end up with the loss of water. So you'd end up with a mass over charge at 70. And then what else are we going to see? We're also going to see an alpha cleavage. So let's go back here. Let's do the loss of the water first. So maybe I'll just do it on this side. I'll do it in blue since it's loss of water, right? So did I put a mass over charge of 18 when I meant to put 88? Mr. Dion's got water on the... Can't stop thinking about mass over charge of 18. So anyhow, so loss of water. So we'll put here loss of H2O, which would be M minus 18. So that means we should see something with a mass over charge of 88 minus 18, which gives us a mass over charge of 70. Now, what would that look like? Let's go back here and see what it would look like. So what you do is you lose water and you just end up making an alkene from the alpha carbon where the hydroxyl was to one of the beta carbons. So since this molecule has symmetry in it, it's symmetrical around this axis, it wouldn't matter where you drew the oops, am I losing too much stuff here? Anyhow, it wouldn't matter where you drew the double bond, but you would end up with something that would look like this. Okay, so this would be your radical cation that you would end up with after you've lost water. I'm not going to ask you to draw something like this, but if you want to practice drawing the fragments, this is something that Mr. Geiger might get you to do in the lab, or I might get you to do in the lab if you take the organic chemistry lab with either he or I. And the next thing is an alpha cleavage. So an alpha cleavage, let's just write here alpha cleavage. And remember that this is our alpha carbon, this is a beta carbon, and this is a beta. You can see that it's symmetrical on both sides, so we'll just do one of them. So we're going to break this bond. That means we're going to lose 29 because we're losing the ethyl radical. So we'll put here alpha cleavage, loss of ethyl radical, which again is M minus 29, like that. So if we take 88 and we subtract 29 from that, that means we should see something with a mass over charge that's equal to 59. Now, what would that look like? Again, I'm not going to ask you to draw the fragment, but if you want to practice drawing what it would look like, it would look something like this, where you would have something that looks like this, okay? And this would, of course, this has a positive charge right here. So that would be what you would see. But again, I'm not going to ask you to draw this, and I'm not going to ask you to draw this. The main thing that you would want to know is the loss of water or the alpha cleavage. And if you want to practice drawing fragments, you can totally do that, okay? I'm even looking at my notes on my desk right now, and it says, will not be asked to draw fragments. Just know how to recognize, you know, what kind of what would you lose? You would lose M minus 18 for the loss of water, and you would lose M minus 29 due to your alpha cleavage. And there you have it. So that's the kind of fragmentation concepts that we need to know for Organic Chemistry 1. And that brings us to the last section of this chapter. If you go to, where am I here? In the table of contents. So we skip sections 14.13 to 14.15. So skip, we're going to skip 14.13 to 14.15. That deals with mass spec of biomolecules and also GCMS, gas chromatography, mass spectrometry, and high resolution mass spec. If you want to read those, whenever I skip a section, if I skip multiple sections, of course you can always read it. It's the land of the free. I mean, if you just want to do that as an FYI thing in your own time, no problem. I mean, the more you know, the better off you are, right? So let's see here. The last section that we're going to be concerned with deals with degrees of unsaturation. Sometimes we call this the HDI, and sometimes we call it the, I'll put here now, or we call it the U for just degrees of unsaturation. HDI stands for hydrogen deficiency index, and I think I might have that written on another slide, but if I don't, I'll scribble it down somewhere for you. Okay, so where are we? We've talked a lot about radical cations, molecular ions. And what's interesting is that a lot of times you can take a molecular ion and you can figure out a way to get a molecular formula from it. And remember, the IR can determine functional groups, and so that can be helpful too in determining the structure of a compound. In fact, when an organic chemist synthesizes a molecule for the first time, she or he is not just going to run an MS. They're not just going to run a mass spec. They're not just going to do an infrared spectrum. Normally, what a scientist would do is run a mass spectrum, an infrared spectrum, and then they'll also do other means of spectroscopy as well, things like NMR, what we're going to cover in chapter 15. So we kind of throw the whole kit and caboodle at it so that we can unequivocally elucidate or identify or determine the structure of a molecule. All right. Well, something that you might remember from earlier on, way back in chapter 4, was that alkanes have this general formula, CnH2n plus 2, right? Let's imagine you have, let's imagine you have nonane, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is nonane. Nonane, it has a formula of C9. Now it's fully saturated, it's an alkane, so it should have 2n plus 2 carbons. So that would be 20 carbons, right? 2 times 9 is 18. Plus 2 gives you 20. So it's C9H20. Let's count here. I'll just put little blue marks where the hydrogen should be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Wow, it works. All right, so that is the formula that we use for a saturated hydrocarbon. You cannot have more than 2n plus 2 hydrogens in an organic molecule. It's impossible. Cannot have more H's. Sometimes I'll teach nursing chemistry, and I remember in one of their final exams there was a question about, which one of these molecular formulas is unreasonable, and one of them said C4H12. And what the students had to put together is that if you have C4, the maximum number of hydrogens you could have would be 10, 2n plus 2. This is impossible. Impossible. So that's kind of the take-home message from that. You need to know the maximum number of hydrogens in a saturated hydrocarbon is 2n plus 2. Well, what if we have unsaturation? Where does unsaturation come from if we don't have the maximum number of hydrogens per carbon atom in a compound? It comes from one of two things. It can come from a pi bond, so it comes from a pi bond, or a ring. Now, students always remember the pi bond. They never forget it. But sometimes they'll forget a ring, and I'll be sure to point that out to you. So let's say you have a double bond or a triple bond. It says for every degree of unsaturation, the number of hydrogens is reduced by 2. Let's say we have pentane. This is fully saturated. So we go from the alkane, which is pentane, and then we go to an alkene, and this is called 1-pentene, but you can see it's got 1 unit of unsaturation. So what did we do? We lost 2 H's when we made one double bond. And then similarly, when we put in a second double bond to make an alkyne, we lost 2 more H's. So lost 2 more H's, and now you've got C5H8. And so the general formula of an alkene is CnH2n, and the general formula for an alkyne is CnH2n minus 2. Now, I said it could either be a pi bond or a ring. Check this out. Let's say I have there. I can't even tell. Let's say I had a 5-membered ring like this. 1, 2, 3, 4, 5. I have 5 carbons, C5. How many hydrogens do I have? I have 10. Right? So the generic formula for a cycloalkane is also CnH2n, which is the same as that for an alkene. So we lost 2 hydrogens for the double bond, or you lose 2 hydrogens for a ring. There we go. So that covers where units or degrees of unsaturation come from. But let's take a look at a molecular formula like C4H6. How many degrees of unsaturation do we have here? Well, if we have Cn is 4, this would be H2n minus 2, right? 2 times 4 is 8, minus 2 gives you 6. So that means we have 2 degrees of unsaturation, like an alkyne. But remember that each degree could come from a double bond or a ring. So what does that mean? We could either have 2 double bonds. This counts as a unit of unsaturation, so 1, 2. You could have them conjugated. They could be accumulated like this. So we have 1, 2 here. What else? You could have a triple bond because you've got 2 pi bonds in every triple bond. You could have 2 rings fused together like this, or you could have a ring and a double bond. So all these different possibilities. So just because you have the molecular formula of a compound doesn't necessarily mean you have the structure. Okay, but what if you took this compound and you ran the IR, and then you saw that you had an absorbance at around 3,300 centimeters to the minus 1? That would mean that you have a terminal alkyne like this. And so that is the kind of rationale that we want to take. All right, so 1 degree of unsaturation equals 1 unit on the hydrogen deficiency index. And so sometimes I'll say U for unsaturation, and other times I'll just say HDI. Now, when you're trying to calculate the HDI, and it can be calculated using a very straightforward formula, what do you do if you have an atom that isn't a hydrogen, right? Because sometimes we have alcohols or aldehydes or ketones, whatever. Well, if you have a halogen in your molecule, you treat it just like it's a hydrogen. So it doesn't affect the HDI at all. All right, so this compound here, which is C2H5Cl, is the same thing as C2H6. A halogen doesn't affect anything. You treat it just like it was a hydrogen. An oxygen also doesn't affect the HDI at all. You can see that this is C2H6O. It's the same thing as C2H6. It doesn't change anything if you have an oxygen, so that's kind of neat. But if you have a nitrogen in your molecule, it increases the number of expected hydrogens by 1. So this compound is C2H1234567, excuse me, N, but it's the same thing as C2H6. So for every nitrogen, you have to remove 1 hydrogen. So you'd have C2H6, right, which is shown over here. Now, if you're wondering, is there a formula I could use? The answer is yes, there is a formula, and the formula is right here. HDI, which is the same thing as, we'll put here, or U, is 1/2 multiplied by 2 times the number of carbons plus 2 plus the number of hydrogens, subtract the number of plus the number of nitrogens, subtract the number of hydrogens, subtract the number of halogens. Remember the X represents the halogens. And there you have it. And that's the formula that you can use. Now, I don't, I mean, I've done this for a long time, of course, so I don't use the formula a whole lot. I have some different strategies that I use. But when you're learning the subject, this is the best way to do it. So let's take a look at a problem. It says calculating the HDI can be very useful. Let's say you have something that has an HDI of 0. That means the molecule doesn't have any rings, no double bonds, no triple bonds, nothing. So let's see if we can calculate some HDIs. I'll remind you of the formula. HDI is equal to 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens, subtract the number of halogens. So let's try the first one. We've got C6H10. So the HDI is going to be equal to 1/2 2 times the number of carbons. So that's 12 plus 2 plus the number of nitrogens, which is 0. Subtract the number of hydrogens, which is 10. and then subtract the number of halogens, which is 0. So if we take 12 plus 2, that's 14 minus 10. 14 minus 10 is 4 times a half, which gives us an HDI of 2. And so for this compound, we could either have a ring and a double bond, a triple bond, 2 double bonds, or 2 rings. If I give you a second, could you try and calculate this one here? HDI is equal to something. Could anybody get that one? Again, if you need a calculator, no problem. Did anybody get an answer for this one? Yeah, thanks, Nicole. Yep, the answer is 1 for this one. If you do the next one, it's all in a similar vein. So HDI for this one, we do 1/2 times. So we take 2 times the number of carbons, which is 10 plus 2. So that's 12 plus the number of nitrogens. That's 1. That's 13. Subtract the number of hydrogens. 13 minus 9 is 4. 4 times a half is 2. And so our HDI is 2 for this one. And you do the exact same things for the next one. I'll just write down the answers in the interest of time. We have an HDI equal to 1, and we have 1 over here. Now, you can even do this for like a gigantic molecule. I mean, something that's really huge. Let's say you had C17H19NO3. What would the HDI to this be? Looks complicated, but it's not. We do the same thing. We say that our HDI is equal to 1/2 times 2 times the number of carbons, so that's 2 times 17, plus 2, plus the number of nitrogens, which is 1, subtract the number of hydrogens, which is 19, subtract the number of halogens, which is 0. So we take 2 times 17, which gives us 34, plus 3, that gives us 37, subtract 19, that gives us 18, and then we multiply that by 1/2, and we end up with an HDI of 9, just like that. So I recommend that you memorize formula, because it will not be provided to you on a quiz or a final exam. All right, and that covers the entire chapter on infrared spectroscopy and mass spectrometry. Yeah, if you go back in the slides, Angel, it tells you